Right, so here example 7. Given a sequence A of n defined as follows. So here we have a recursion definition right here. So a1 is equal to 1 and an is equal to n times an minus 1. Then we need to prove that a of n is actually equal to the factorial function evaluated at n for all natural numbers n. Alright, so typically right here I'm going to use induction. So first of all, we're going to write the base case. Now the base case right here will be the smallest possible domain for n, which is the smallest natural number, since it is defined for all natural numbers. So here we can set n is equal to 1 as our base case. So here we have a of 1 is equal to 1 based on our first definition, which is actually equal to 1 factorial if you notice. So the base case is true. Now for the induction hypothesis, we can suppose this is true for some n equals k value, and then we need to prove this also applies for a certain n is equal to k plus 1 value. Alright, so let's just write our definition in terms of k plus 1 right here. So we have a of k plus 1 is actually equal to, well, we suppose that a of n is equal to n factorial, so we can suppose this to be k plus 1 factorial. Notice that we can separate or rewrite this in a different way. So notice this is equal to k plus 1 factorial, k plus 1 times k factorial. Notice I just factor out a k plus 1 and then leave the k factorial behind. However, notice that k factorial is actually equal to the a-kth term in this sequence. So it will be k plus 1 times a of k, which is actually true from our definition right here. So here we have proven the induction hypothesis is true and we are done. So this is a I would say very basic type of induction problem, and usually in Olympiad problems it is not very straight to the point, but it is sometimes needed in like a middle of a problem when you're trying to solve something. And this ends this video.